Hey everyone, welcome to this third lecture in our series on imitation learning. I'm Sanjivan Chaudhary, a research scientist at Aurora and soon to be assistant professor at Cornell. Today, we'll talk about the role of interaction in robot learning in general. Unlike in supervised learning, where we get data up front, robots must interact with both humans and the environment to acquire data for learning. But what makes for a good interaction? To find out more, let's begin with the world of supervised learning, where truly everything is awesome. Let's pretend you are the CTO of a new startup that aims to do self-driving for race cars. Now, given your machine learning background, your approach, contrary to others in the field, is to solve this problem by collecting lots of data of an expert race car driver and learning to imitate that driver, which sounds like a great idea. So you go get an expert driver, ask them to drive round and round a track, um, and you then collect this data. So what does the data look like? Here the data would be pairs of states and actions, where state is the pose of the robot and action is the steering angle and brake and throttle. Now these state actions are actually drawn from a complex joint distribution. And you take great pains to ensure that you're drawing samples IID from this distribution. You then save all of these samples in a database, which is then shipped to a robot learning team. Interestingly, in supervised learning, once you've collected the data, there's really no need to further interact with the world. So your expert driver steps away and goes home, and now you're only left with this data set that you collected. Now, your robot learning team is essentially solving a classification problem where given states, you're trying to classify which action should the robot pick. In other words, you're building a policy. And the standard way to do this is to minimize empirical risk, where you're searching over the space of policies and picking the one that has the lowest risk on your training dataset. You even do your due diligence by evaluating this policy on a held out test dataset and verifying that the policy has a low risk on that dataset. Now, the great thing about supervised learning is it comes with guarantees. For example, the true risk of a policy on the joint distribution of state action samples is within epsilon bound of the empirical test risk that you observed with high probability. And the number of samples you need depends on the complexity of your policy class, on epsilon, and on the probability delta. And so your machine learning team comes back saying, this is great, we have a policy that's ready to ship, problem solved, job done. But reality hits when you ship this policy back into the real world. So when you execute this policy on the robot, it seems to initially be doing fine till it makes a mistake, and then it enters a state it's never seen before and makes more mistakes and keeps going till it spirals off the track. So what went wrong? In a nutshell, we failed to account for the fact that once a robot made a mistake, it would visit states it has never seen before and continue to make mistakes thereafter. In other words, the distribution would diverge from the training distribution, rendering all the guarantees of supervised learning utterly meaningless. Now, there's no real reason to be disheartened because this phenomenon is not restricted to the story, but is in fact a much more deeper truth about robot learning. That robots need to interactively acquire knowledge by interacting with both humans and the environment. So let's take a look at a more abstract formulation. We have a robot that is reasoning over a space of policies that map states to actions. And we have the world that provides labels. In other words, what is the optimal action to execute at any given state? And the key thing is that the robot must interact with the world. The world provides a pair of states and optimal actions at each of these states, and the robot queries the world by executing policies to visit various states. And we lay out a set of core assumptions. The first one being the most important, that is, there exists a policy pi star in the robot policy class that is human-like, that is good enough. If we were to execute this policy, we would all be happy. Second core assumption is that the initial knowledge that's provided to the robot is insufficient to identify pi star. So the initial set of state action pairs, shown in blue, provided to the robot is not enough to collapse the uncertainty about pi star. That is, there are a lot of bad policies that are consistent with this initial set of data. And so the third assumption is the robot needs to interactively query the world to get more data. It does so by executing policies that visit newer states and receives actions in each of these states it visits. And every time it receives this new sets of additional knowledges, it's able to sort of collapse the space of policies by eliminating bad policies. And this process continues until the uncertainty has been collapsed sufficiently around pi star. Let's now take a look at how this abstract framework plays out in the concrete setting of imitation learning and system identification. Now, at the face of it, they may sound very different, but I'll convince you that they're actually the same problem underneath the hood. So in imitation learning, you have a robot that is interacting with a human. The robot interactively asks the human for the correct action at states that the robot may visit. How does this interaction go? The robot begins by executing some initial policy. Maybe this policy was trained using supervised learning. So once it executes this policy, it visits a various set of states. The robot then asks the human to label these states. Human goes in, shows what the correct action would have been in each of these states. This data is then used to update the policy, and the process repeats. The robot executes the policy, human provides actions, robot updates the policy and continues till it has learned a good policy that imitates a human. So that is, in a nutshell, imitation learning. Now let's move on to system identification. In this setting, we're not trying to learn the policy. Instead, we assume that we already know the cost function we wish to optimize. For example, stay on the track. Instead, we are trying to learn the dynamics of the system. Given the current state and an executed action, what is the most likely next state the robot can visit? If we know both the cost and dynamics, this problem reduces to simply solving a planning problem or an optimal control problem, where the robot is solving for a policy that minimizes the cumulative costs of state actions that the robot's likely to visit according to its dynamics. So in the system identification setting, the robot isn't so much interacting with the human. Instead, the robot is interacting with the physics of the world. How so? Well, the robot is executing a policy and visiting state action sequences. It's then asking the world, given a particular state and action, what is the next state that I'm likely to visit? Which it already knows purely by executing the policy, right? So it then collects this sort of state action next state tuple, and that becomes a data set. This data set is then used to update the dynamics, and the robot then calls the planner to get a new policy, get new data points, update the dynamics, and so on until it solves the problem. Warning: naively training policies only on the latest data can destabilize interaction. What do we mean? Let's take a closer look at the case of imitation learning, where you have a robot interacting with the human. The robot sends a policy pi hat to the human, and the human labels this policy, labels states visited by this policy. Now you can imagine this labels inducing a loss function L pi on the space of policies. Let's assume the robot is greedily minimizing this loss, this latest loss. How does this interaction play out? Well, let's assume the robot begins with an initial policy pi 1 hat. And so it drives off the track and visits a new set of states. Human goes and labels the state. Let's assume these labels induce a loss L1 pi. Now the robot chooses to greedily minimize this loss, right? Do well on the demonstrated actions, and comes up with a policy pi 2 hat that makes a whole new set of mistakes. So it's erroring too far on the other side. Human goes forward and labels these new states, and you get an L2 pi, which the robot chooses to greedily minimize. And so it ends up with a policy pi 3 hat. Interestingly, looks exactly the same as the initial policy pi 1 hat. And this sort of creates an infinite loop where the robot either errors too much to the right or too much to the left. Now, this might remind you of a game of whack-a-mole, where by being greedy, the robot does really well on one loss, only to do terribly on another loss. And intuitively, this makes a lot of sense because the robot keeps forgetting previous losses by being greedy and focusing only on the current loss. So this begs the question, what is a reasonable interaction strategy that does not lead to this sort of infinite loop, destabilizing like behavior? Our key insight is that interactions must be no regret. What do we mean by this? Well, let's first begin by accepting the fact that what's really going on is that the robot is playing a game with the world. So, in this game, the robot plays a policy pi 1, and the world acts like an adversary and sends back a loss L1. And the robot plays a policy pi 2, and the world sends back a loss L2. And this process continues on and on and on. Furthermore, we make no statistical assumption about these losses. They could even be adversarial. Finally, we need to introduce this notion of regret, which essentially means how sorry is the learner for not playing a particular policy pi star in its policy class all along. More formally, regret R, or given a sequence of policies, equals a difference of two terms. So the first term is the cumulative losses experienced by the learner during the game. So you sum over all iterations, and at every iteration, you take the policy pi that was played and the loss li that the adversary returned, and add up these terms. The second term is how well the best policy in your policy class does on the cumulative losses. So after you get all the data, you look at your policy in your policy class and you pick the one that has the minimum cumulative loss. The difference of these terms is the regret. So our desiderata is to pick a sequence of policy pi I that incurs low regret. And intuitively, this means do as well as you can as if you had all the data up front. In particular, we want to be no regret. That is, on average, drive regret to zero. In other words, an average do as well as if you had all the data in advance. Why do we really care about regret? I mean, it seems like what we should care about is, given a sequence of policies, like pi 1 to pi n, what is the best policy in that sequence? What is the policy that has the lowest loss that it itself induces? Well, if we write down this expression, we can see that we can upper bound this term by the average loss of that all policies experience, because the min is less than the average. We can then add and subtract a term, which is the the cumulative loss of the best policy in hindsight. Now you can see that term on the left is in fact the regret, the average regret. Term on the right is simply the best policy in hindsight. So if we can drive regret to zero and be no regret, so if we can upper bound the objective we care about by epsilon class, which is how well the best policy in my policy class does on the cumulative loss. And so we end up with a guarantee that at least one policy from our sequence must be pretty good. So how do we achieve no regret? The way I think about no regret, largely inspired by Drew Bagnell, is that an algorithm must satisfy two properties. Number one, given enough data, the algorithm must return the right answer. That is, it must be statistically consistent. And number two, it must be sufficiently stable. Given small perturbations in the training data, it mustn't change its answer. Now, the simplest approach you can think of, that is online gradient descent, is a no-regret algorithm. What is online gradient descent? It proceeds iteratively, where each iteration you play theta I and receive a loss Li. And then you take a step along the descent direction, where the step size is 1 over the number of iterations. So what does this look like in the landscape of loss functions? Well, you play an initial theta and you receive a loss L1, and then you take the gradient of that loss at theta and you move a tiny step, play theta 2, receive another loss. Maybe this loss completely contradicts the first loss, so now you take a gradient of this loss and keep going. And you can show that for strongly convex loss functions, the regret of this algorithm, Rn, takes the following form. It's g squared, where g is the maximum gradient, over 2 alpha, alpha is the step size, and times the log of the number of iterations. In other words, the average regret is log n over n, which goes to 0 pretty sharply. A second more general algorithm is follow the leader, or FTL. So at every iteration, you're playing a policy pi I and receiving a loss Li. And then to update policy pi I plus 1, you minimize the cumulative losses that you've seen thus far. So you add up all the losses and minimize the sum. The way to think about this is that you have a database of loss functions. You initialize the database with a loss, train your policy, receive a new loss, add it to the database, and update your policy, and keep going. Now, interestingly, this algorithm as well shares a very similar looking regret bound as online gradient descent, where the regret bound is L squared over 2 sigma, L being the Lipschitz constant of the loss function, and sigma being the strong convexity coefficient, times log n. So the average regret log n over n goes to 0. To see the proof of this theorem, I highly recommend checking out this paper by Kakade and Schwartz that leverages the principles of duality to derive these sharp bounds for online optimization. So armed with the follow the leader algorithm, let's jump back into our two settings. Let's start with the imitation learning setting. So the first step is to initialize the loss. So you collect initial data using human demonstrations, and that becomes your first loss function, L naught pi. We're going to use this data set to train our initial policy pi 1. Then we'll proceed iteratively, where at each iteration we are going to roll out pi I to get states visited by the learner. We will then ask the expert to label these states. So as soon as they do that, we get a new loss function, Li pi. Then follow the leader will ask you to aggregate losses. So we're going to aggregate this to a data set. And finally, we're going to use this aggregated data set to update our policy. And you can see that this is simply the step where your new policy is minimizing the cumulative losses that it has seen up until that point. Then the process repeats itself. So you roll out this policy, get new states, get labels, and keep going until you've solved the problem. And this algorithm has a name. It's called Dagger. It's the very same algorithm that was published by Ross et al. In 2011. Okay, so let's now move to the domain of system identification. We'll see how it'll proceed in the exact same manner. So, as you recall, in this paradigm, we are trying to learn a model of our system instead of the policy. So we're going to collect some initial data by driving the car round and round. So here data is state, action, next state pairs. And then we're going to train a dynamics model based off this data. Then we'll proceed iteratively, where at each iteration we solve optimal control using our model. We then, so this would look like solving for a policy that minimizes cumulative cost, where states are sampled from a model. Then we roll out this policy by I to collect new state, action, next state pairs. This is then aggregated to a data set, and we train a new dynamics model on this aggregated data sets. You can think of repeating this process over and over again until we have solved the problem. So this too is another paper by Ross and Bagnell. It's called Agnostic System Identification for Model-Based Reinforcement Learning. And with that, we're at the end of our talk. So to recap, the key challenge that we talked about today is that for robot learning, we do not get data up front. We must interact with the world. So this is where it diverges sharply from the world of supervised learning. We also saw that interaction could be of two forms: interaction with the human, which we call imitation learning, and interaction with the environment, which we call system identification. We saw that no regret is a reasonable strategy for interaction because you're doing as well as you can, as if you knew all the data up front. Finally, on a parting note, I want us to think about the assumption we made about adversarial losses. Can we do better if we relax this assumption? For example, the loss function li pi may change predictably from iteration to iteration. Or we may even have a prior over this loss, for example, in a Bayesian setting. Leveraging these assumptions will allow us to quickly converge on the optimal policy. In either case, these are open questions left for another day. Thank you for your time, and be well.